I'm Greg, Lab Group 3B on Tuesday morning. In Lab 10 we're taking a look at imaging system calibration with a CCD camera. We'll be using it with a wide-angle fisheye lens and a zoom lens as well. But before we can do that, we need to measure a few key parameters. First we take a look at is the size of the CCD detector using a microscope here to scan across the detector. We calculated the size of the detector and then used the number of pixels basically to come up with a pixel size of approximately 11 microns by 11 microns. We then calculated the size of these squares on this checkerboard and on this box as well, which we'll be using later. To calculate field of view, we put a ruler on a mount, brought it into focus, and then measured the distance from the ruler to the camera. We used the horizontal distance here across the ruler to then calculate field of view for both the zoom lens here and the fisheye lens here. For the fisheye, we ended up with about 162 degrees total field of view, and for the zoom lens, we had a total field of view of about 46 degrees.
Hello, my name is Kevin, and in the next part of the lab we wanted to calibrate the camera for using both lenses. So in order to do that, we used the square grid here, and we kept it at a certain distance away from the lens and took pictures of it at different orientations. And we then loaded the images onto the computer where we could use some software in order to calibrate the distortion and other values possible. So once we have the images loaded onto the computer here, we use the MATLAB software to view the images and select certain regions in here, and then we input the number of squares that we select and the distance between the squares, and then we can input a certain amount of distortion that we think is present until it looks clear that the image is corrected properly, and that'll calibrate the amount of distortion in each one. So after calibration, our goal was to end up with a pixel error of around 0.2 for the fisheye lens and around 0.1 for the other lens. What we ended up with was about 0.23 for the fisheye lens, so it was pretty close to our goal, and 0.108 for the other lens. The distortion in both was dominated by the first and second terms, and of course in the fisheye lens, as expected, it was much greater than the other lens. Here's an example of one of the images we took uncorrected on the left compared to after the calibrated correction. You get the image over here on the right. So we corrected all the images that we took, and we can tell that the distortion was corrected because the straight lines that we know should be straight because of the calibration square that we used are curved in the uncorrected image, but in the corrected one the straight lines are perfectly straight as expected. Pause.
For the next part of the lab, we were told to image a kind of a slanted bar image here, and then use that along with the previously calibrated camera in order to determine the MTF of both lenses. So here we have the fisheye lens, and then if we go back here, this is the zoom lens. You can see, for the most part, despite the fisheye having a greater amount of distortion, both have pretty much the same performance measures for low spatial frequencies, both having a null at around 0.3 cycles per pixel. Pause.
Hi everyone, I'm Thaw, and I'm going to continue with the last part of the experiment. So after we calibrate the camera, we're going to image a box like this, and we're using the same camera and the same zoom plane. From these, we're going to feed the data back to the system and using the calibration coefficients to correct the image, and then we go to use the functions name extrinsic to determine the rotational matrix. This is the rotational matrix, and the difference between the two numbers going to give us the angle between the two planes. And the calculations turn out to be 97 degrees, which is really close to the ideal, which is 90 degrees. So it's really close, and it's a well calibration system.